Hello students, today we are going to cover moving charges and magnetism JEE PYQs. This is a disclaimer. The learning objectives from our today's topic. After this lecture you will be able to understand how magnetic fields interact with moving charged particles, determine the direction of magnetic force using fundamental principles, calculate the magnetic fields produced by a current carrying conductors in different configurations, analyze the motion of a charged particles in uniform magnetic fields and their relationship with charge, mass, and kinetic energy, and apply electromagnetic force concepts to solve practical problems involving current carrying conductors in magnetic fields. So our first question, two long straight wires P and Q carrying current equal 10 ampere each were kept parallel to each other at 4 centimeter distance. Okay, so I here is IP here is 10 ampere, IQ here is 10 ampere also, and D here is the distance between two parallel conductors, 4 centimeter. Magnitude of magnetic force experienced by 10 centimeter length of wire P is F1. So we used to calculate the force per unit length on the current carrying conductor, okay, due to other conductor. Now we are going to calculate the force experienced. We are going to determine the force experienced by 10 centimeter length of wire. Okay, so we will multiply it with length of the wire also. So multiply it with 10 centimeter. Firstly we will calculate the force per unit length, then we will multiply it with length, or initially we will multiply the formula with the length. So force experienced by 10 centimeter length of wire P is F1 if distance between wires is halved. Okay, now another condition. If distance between the wires is halved, okay, and current on them are doubled, means current will become 20 ampere and the distance becomes 2 centimeter. Force F2. Now the force on 10 centimeter length of wire P will be F2. Okay, you have to find the relation between F1 and F2. I will give you some time to think about it. Options are 8F1, F2 equal to 8F1, 10F1, F1 upon 10, or F1 upon 8. So let's see the solution. So correct option is A, 8F1. So solution using concept 18.14, given current in wire P. So what is given, we are going to list it. So current in wire P initially IP, which is equal to 10 ampere. Current in wire Q initially IQ equal to 10 ampere. Initial distance between wires D1 equal to 4 centimeter. And length of the wire P for which force is experienced 10 centimeter. Okay, for length, for which length we are going to calculate, we have determined the force F1. So for 10 centimeter of P wire. And initial magnetic force experienced by 10 centimeter length of wire P is F1. Okay. Now another condition, when we halved the distance between the conductors and doubled the currents. So new distance between wires D2 will be equal to half of the initial distance, which is D1 by 2. New current in the wire is I dash P, okay, which is 2 into IP because currents are doubled. So 2 into IP. So new current in wire Q is I dash Q, which is equal to 2 into IQ. and new magnetic force experienced by 10 centimeter length of wire P is, so what is the new force experienced? F2. Okay. Now we have to derive the relation between F1 and F2. So initially force between two wires carrying conductor IQ and IP and IQ is, so force between two straight long current carrying conductors is given by, force per unit length is given by mu naught by 2 pi I1 I2 upon D. This is the force per unit length. If there is, we are going to find the force on a conductor or particular length. Okay, if we are not taking unit length, if we are taking some length, then we have to multiply it by length also. Okay, so force between two wires carrying current IP and IQ is F1. It is given. So a magnitude of F1 will be equal to mu naught IP IQ upon 2 by D. This is force per unit length multiplied by L. So what is L here? 10 centimeter of P. So mark it as first equation. Now distance between wires is now halved and currents are doubled. So force between two wires carrying current now IP dash and IQ dash is F2 equal to mu naught IP dash IQ dash upon 2 pi D2 and multiply by L. Okay, now we have to derive the relation between F1 and F2. What are common things in F1 and F2? Mu naught L 2 pi. Okay, also we have seen initially that I dash P is equal to 2 into IP. I dash Q is equal to 2 into IQ and D2 is D1 by 2. So we have to put all these values in this equation. Okay, so put these values in this F2 expression for F2. Since I dash P is equal to 2 into IP, I dash Q is equal to 2 into IQ and D2 is equal to D1 by 2, then F2 will be equal to mu naught, now 2 and 2. 2 from 2 into IP and 2 from 2 into IQ. They will get multiplied and it will result in 4. So mu naught 4 IP IQ L upon 2 pi D1 by 2. And this 2 is will also go in numerator and 4 into 2 will become 8. So F2 will be equal to 8 mu naught IP IQ L upon 2 pi D1. So this term in bracket, mu naught IP IQ L upon 2 pi D1. What is this? This is F1. Okay. So using one equation. Okay, for expression of F1, we have marked it as one equation. So using that one, this term will become F1. So F2 is equal to 8 F1, which is required answer. Okay. Okay, let's move on to the next question. As shown in the figure, a metallic rod of linear density. What is linear density? Mass upon length. Mass per unit length. Okay, what is volume density? Which is normally we use density, that is volume density. Mass upon volume, that is volume density. This is linear density, which is mass upon length. Okay, so linear density is given 0.45 kg per meter. Is lying horizontally. This rod is lying horizontally on the smooth inclined plane. It is lying horizontally on smooth inclined plane, which makes an angle 45 degree with the horizontal. The minimum current flowing in the rod required to keep it stationary when 0.15 Tesla magnetic field acting on it in the vertically upward direction. Okay, will be. So we have to find the minimum current which will flow through the rod and keep it stationary on the inclined plane. And magnetic field is existing in the region which is vertically upward, which is exactly 90 degree to the base, not to the inclined plane, to the base. Okay, and use G equal to 10 meter per second square, and diagram is also shown. Okay, so this is rod. This is rod. It is placed on inclined plane. Okay, this inclined plane, this plane is inclined to this horizontal base at 45 degree. Okay, this magnetic field is vertical to horizontal base. Okay, so we have to find the minimum current flowing through that rod so that it will remain stationary. Okay, so options are 30 ampere, 15 ampere, 10 ampere, or 3 ampere. So I will give you some time to think about it. Let's see the solution. So correct option is A, 30 ampere. Okay, using concept 18.11. So this concept number is from your formula book. Given linear density of the metallic rod is given, lambda is equal to linear density is denoted by lambda, which is equal to mass upon length, which is equal to 0.45 kg per meter. Angle of inclination of the plane, so we are denoting it as phi, okay, which is equal to 45 degree. Magnetic field strength B is equal to 0.15 Tesla, which is vertically upward, and it is at 90 degree angle to the horizontal base. Acceleration due to gravity G, you can use it as 10 meter per second square. Okay, these things are given. Now, magnitude of the magnetic force on a current carrying conductor is given by. So what, in the presence of magnetic field, this metallic rod is carrying current, so it will experience some force. Okay, so we will use the formula of magnitude of magnetic force on a current carrying conductor. What is that formula? F equal to I L cross B. So we are taking only magnitude. Okay, so F equal to I L cross B mod. So F equal to, this is the formula for magnetic force on a current carrying conductor. Okay, so F I L B sine theta. Okay, so now you can see that magnetic field is in the vertically upward direction and current is flowing horizontally. Okay, you can see current is flowing horizontally and magnetic field is vertically upward. Magnetic field is along y-axis, and this I is in which I is in which direction? Along z direction. Okay, so this B and I is perpendicular. Okay, magnetic field and current is perpendicular because current is horizontal, magnetic field is vertically upward. Okay, so they are horizontal. They are perpendicular to each other. So theta will be 90 degree here. Okay, so ILB sine theta equal to ILB sine 90 degree, which is equal to ILB because sine 90 degree is 1. Angle between IL and B is 90 degree. Direction of magnetic force can be found using right hand rule for vector products. Okay, you can find the direction of force. Align your fingers in the direction of current. Okay, and curl them towards magnetic field. Thumb will give the direction of magnetic force. Now, in this case, you should align your fingers in the direction of current through the rod and curl your fingers vertically upward. Okay, your thumb will give the direction. Your thumb, the force will in this direction and along this inclined plane. Okay, so current will, force will be in the direction of this and along the inclined plane because your fingers are also inclined. When you point your fingers in the direction of current, your fingers will also be aligned along the conductor because metallic rod is placed on inclined plane. So your fingers will be inclined also at 45 degree to the base, and curl fingers vertically upwards or in the direction of magnetic field. So this force will be along this inclined plane and upwards. Okay. So now this is the side view of all the forces and resolution of forces. So figure showing resolution and balancing of all the forces acting on the rod. So this is the rod. This is side view from here, from side. This is the side view of this thing. So current is flowing. This is represented by dot. So current is flowing perpendicular to the plane and inwards. So current is flowing inwards. Okay. So magnetic field is like this, perpendicular to the base, not to the inclined plane, perpendicular to the base. Okay. So force will be in direction this. Okay. Now you can find the direction of force by this thing. Okay. So you can apply the right hand thumb rule now more conveniently. Okay. So it will be align your fingers in the direction inwards, perpendicular to the plane and inwards, and curl them vertically upwards in the direction of magnetic field. This thumb will give the direction of force, and thumb will direct toward this ILB. Okay. So this is ILB in this direction. This is the direction of force, and along the vertical plane there will be component of the force. Okay. So we will resolve this force into two components. One component will be along the vertical plane. Okay. Force will not be along the vertical plane. Force will be in this direction, but a component of force will be along the vertical plane, and one component of force will be perpendicular to this vertical plane. Okay. We can resolve this. This is 45 degree. So this will be 45 degree. So this component will be ILB cos 45 degree. This component will be ILB sin 45 degree. Okay. Force is resolved. Now, rod has some mass. Due to this, there is mg weight always acting in the downward direction, vertically downward direction. Okay. So mg. So now we can resolve mg also. So according to geometry, you can find this angle is also 45 degree. So this component will be along this ILB sin 45 degree. Component will be mg cos 45 degree, and along the vertical plane and downwards there will be component mg sin 45 degree. Okay. You can resolve the forces. Okay. You have also studied this in 11th class, and in almost every chapter there is this concept is being used, resolution of vectors. Okay. So now you are familiar to it. So this is normal force acting vertical to the plane. Okay. So now this normal force is balancing these two forces, ILB sin 45 degree, mg cos 45 degree. But we are not concerned with that. We have to find the minimum current. So we will balance these components. Rod is stationary due to what components? These components that are along the inclined plane. If they are balanced, they are balancing each other, they are equal, then this rod will be stationary. So this mg sin 45 degree should be equal to ILB cos 45 degree. So that rod will remain stationary and don't roll along the inclined plane. Okay. So this diagram is clear. So magnetic force is horizontal and making 45 degree with the inclined plane. So what is the direction of magnetic force? Horizontal, parallel to the base. Okay. And making 45 degree with the inclined plane. Got it? Now from the figure, mg sin 45 degree is equal to ILB cos 45 degree. Okay. So this is the condition for rod to be stationary. After rearranging the equation, we will get I equal to mg sin 45 degree upon LB cos 45 degree. Okay, so I equal to mg upon LB. So sin theta upon cos theta will be equal to tan theta. So sine 45 upon cos 45 will become tan 45 degree. So I will be equal to mg upon lb because tan 45 degree is 1. Okay, after substituting all the values, we will get, so after substituting m upon L, linear mass density, linear density, it will be 0.45. Okay, then the value of G, 10, and upon value of magnetic field, 0.15. After substituting all the values, you will get current will be equal to 30 ampere. Got it? So this is the required result. So minimum current flowing in the rod required to keep it stationary is 30 ampere. Next question. A long conducting wire having a current I flowing through it is bent into a circular coil of n turns. Then it is bent into a circular coil of small n turns. Okay. So two conditions, two situations are given, two cases are given. First case, a long conducting wire of carrying current I is given. Okay. So firstly, it is bent in the form of a circular coil of capital N turns. Then after, it is bent in the form of circular coil again, but of small n turns. The length of the wire is same. So total length of the wire will remain same. Okay. Only number of turns through which we are bending the straight wire into circular coil is different, due to which radius will also be different. Okay, we will see how. The magnetic field is calculated at the center of the coils of both the cases. In both cases, we have calculated the magnetic field at the center of the coil. The ratio of the magnetic field in first case to that of the second case, we have to find. Okay, so options are n square ratio small n square, capital N ratio small n square ratio capital N square, or n ratio capital N. Okay, these are the four options. So I will give you some time to think about it. So A is the correct option, capital N square ratio small n square. Okay, using concept 18.5.1. So magnetic field B at the center of a coil carrying current I and radius R having n turns is given as. Okay, so there is a formula for magnetic field at center of the coil having n turns carrying current I and of radius R, which is given by B equal to mu naught N I upon 2R, which we have found using Biot-Savart law. Okay, so B equal to mu naught Ni upon 2R. This is the formula for magnetic field at the center of the coil. Okay, so diagram for two given situations. So that two cases that we are given in the question, we are going to represent two cases in the form of a diagram. So this is the required diagram. Okay, so first coil, in the first case carrying current I capital N having capital N turns. Okay, so this is L1, not I1. Okay, this is IN, this is L1. Okay, so don't confuse it with I1. Okay, L1. Now length in both the cases is same. Length of wire is that long conducting wire we are taking in both cases is same. Okay, so in first case, what is the length of the wire? L1, which is equal to number of turns into 2 pi r. Okay, so what is 2 pi r? Parameter of a one circle of coil, one turn of coil. There are n number of circular coils. So perimeter of one circular coil multiply by n. This is the total length of the wire L1. In second case, L2, which is again equal to 2 pi small r, which is perimeter of one turn. And how many number of turns are there? Small n. So length of the wire is small n into 2 pi r. Got it? So length of one turn, or we can say perimeter of one turn, is 2 pi small r into small n number of turns. So it will result in total length of the wire from which we are making circular coils. This L1 is equal to L2. Okay, because we are using same long conducting wire for both the cases. In both cases, same length of wire is taken into consideration. That is L1 equal to L2. Okay, so N, capital N into 2 pi r will be equal to small n into 2 pi small r. Okay, from here we will find the relation between radii of both the circular coils. Okay, so small r upon capital R will be equal to capital N upon small n. Okay, so this is the ratio of radii. We are going to use it further. Okay, so mark it as first equation. Small r upon capital R is equal to capital N upon small n. Okay, for first case, magnetic field at the center of the coil carrying current I n, which is equal to I given in the question. Okay, having n turns and radius r. So B1 will be magnetic field at the center of the first case will be B1 equal to mu naught n I upon 2r. Okay, so for second case, magnetic field at the center of the coil carrying current I small n, which is equal to I also given in the question, both carrying current I, having small n turns and radius small r. So B2 will be mu naught small n I upon 2r. Now we have to find the ratio of magnetic field in the first case to that of the second case. So B1 upon B2. So ratio of magnetic field in first case to that of the second case is B1 upon B2 mu naught capital Ni upon 2 capital R upon mu naught small n I upon 2 small r, which is equal to 2 mu naught capital N I small r upon 2 mu naught small n capital I capital R. Okay, so I and I 2 mu naught and current I will get cancelled out from the numerator and denominator. Only we are left with capital N upon small n and small r upon capital R. So after simplifying, we will remain with B1 upon B2 will be equal to capital N upon small n, small r upon capital R. Now we have found the ratio of small r upon capital R, radii of ratio. Okay, we have found in the previous slide. So we are going to use it. So using one, B1 upon B2 equal to capital N upon small n, capital N upon small n. Okay, so B1 ratio B2 will be equal to capital N square ratio small n square. Okay, got it? This is the required answer. If we are going to take same length of wire and wound it in the form of bend it or wound it in the form of circular coils of different number of turns, their radii will also be different. Okay, so that's why it is capital N square ratio small n square. Okay, next question. As shown in the figure, a long straight conductor with semicircular arc of radius pi by 10 meter is carrying current I equal to 3 ampere. Okay, this is similar question as given in your NCERT example also. We have done in the theory section. Okay, this is similar question. The magnitude of the magnetic field at the center O of the arc is, the permeability of the vacuum or free space is given 4 pi into 10 to the power minus 7 Newton per ampere square. Okay, so this is the diagram shown. There are two straight conductors on the both ends of semicircular arc. Okay, they are long straight conductors. And there is one semicircular arc. We have to find the magnetic field at the point or center O due to all these conductors, due to all these two straight conductors and due to this semicircular arc. Options are 3 microtesla, 1 microtesla, 4 microtesla, or 6 microtesla? I will give you some time to think about it. You can solve this question and comment and write the correct answer in the comment section also. Okay, so then you can verify when we are doing solution. So do participate in the class. So correct option is A, 3 microtesla. Okay, using concept 18.2 and 18.5.1. So what are given? So initially when you are solving problem, you have to list all the things that are given in the question. It will help you to analyze or visualize what is the formula that is applicable in this question and what is given. Okay, so you have to list all the things that are given in the question. So what is given? Radius of the circular arc r equal to pi by 10 meter. Current flowing through wire I equal to 3 ampere. Mu naught permeability of free space is given 4 pi into 10 raised by minus 7 Newton per ampere square. Okay, so these things are given. Now another diagram, we are marking this straight conductor as first segment and this semicircular arc as second segment. Okay, so 3 ampere current is flowing through all the segments. According to Biot-Savart law, what is magnetic field due to conductor carrying current? dB is equal to mu naught by 4 pi I dl cross r mod. We are taking magnitude only upon r cube. Okay, for straight conductors, these straight conductors, one and similar to that one on the other side. So due to which, if we are going to find the magnetic field at this O, so due this dl vector, if we are taking small dl vector on this conductor, okay, so this dl vector is having direction towards this center, and we are also pointing a position vector from this dl to this O vector. So this dl vector and this position vector from this dl to this O point is parallel. Okay, and in this case, dl vector is in this direction of current, and we are pointing or marking a position vector from dl to this O point. So dl, direction of dl vector and the position vector from dl to this O will be having opposite direction, so they are anti-parallel. So for both the conductors, dl and r, for straight segment 1 and its identical straight segment on the other side, this, are parallel and anti-parallel. So for both these segments, dl and r are parallel and anti-parallel respectively. Okay, due to which, therefore dl cross r will be equal to 0, because dl cross r is equal to dl sine theta. So they are parallel or anti-parallel, means theta is 0 or 180. So sine 0 or 180 both are 0. So dl cross r will be 0. Straight segments do not contribute to net magnetic field at O. Okay, so these straight segments are not contributing to net magnetic field at O point. Okay, so net magnetic field at O point is only because of the semicircular arc. Okay, so but magnetic field due to segment 2, that is semicircular arc, is non-zero. Okay, so magnetic field due to semicircular arc is given B equal to mu naught I upon 4r. For complete circular arc, it is given mu naught I upon 2r. For semicircular arc, it is mu naught I upon 4r. So which is half in magnitude as compared to the complete circular loop. So now substituting the values. So B is equal to 4 pi into 10 is by minus 7 into 3 upon 4 into pi upon 10. So B is equal to 3 into 10 is by minus 6 Tesla, which is 3 micro Tesla. So 10 is by minus 6 is micro. So 3 micro Tesla, which is the required answer. So the net magnetic field at the center O is 3 microdesicel. Got it? Now next question. An electron is moving along positive x-axis. Okay, so this is more like conceptual question. Okay, so electron is moving along the positive x direction. If the uniform magnetic field is applied parallel to negative z direction. Okay, so you have to think about the directions accurately. So positive x-axis means velocity is in the direction plus I cap. Okay, uniform magnetic field is applied to the negative x-axis means B is in the minus k cap, is in the direction minus k cap. Then 5 statements are given. First statement is the electron will experience magnetic force along positive y-axis, or the electron will experience magnetic force along negative y-axis. Electron will experience force C statement is electron will not experience any force in the magnetic field. D statement is the electron will continue to move along the positive x-axis, and E statement is the electron will move along circular path in the magnetic field. Okay, so choose the correct answers from the option given below. A, C and D only. Which are the correct statements? C and D only, B and D only, B and E only, or A and E only. Okay, so I will give you some time to think about it. So answer is C. Correct option is C. B and E only. So B statement and E statement are correct. Okay. Using concept 18.9, the electron is moving along positive x-axis. Therefore, velocity vector of electron is along positive x-axis. Means V vector is equal to V I cap. Okay, so velocity is in the direction of positive x-axis. So it is V I cap. Okay. The uniform magnetic field is applied parallel to the negative z-axis. Therefore, magnetic field vector is minus j cap. So B vector will be equal to B minus k cap, minus z negative z-axis. So minus k cap. So B vector is equal to B minus k cap, which is equal to minus B k cap. The magnetic force F experienced by a charged particle in a magnetic field is given by Lorentz force, which is equal to F vector is equal to Q V cross B. So magnetic force experienced by a charged particle is given by Lorentz force law. Okay, which is F Q V cross B. Also there is QE in the formula, but there is no electric field. So this part of the formula can be neglected. So F equal to Q V cross B. Okay, now we know electron has a negative charge, which is Q equal to minus E. Now put all these values in the expression of force, substitute all the values V vector and B vector into the force equation. So F vector will be equal to Q V cross B. So Q is minus E, V is V I cap cross minus B K cap. Okay, so it will result in, there are 2 minus in the equation. Okay, so it will result in F equal to minus E, and V and B are magnitudes, so they will get out of the cross product. So VB minus E minus VB. In cross product, it is I cross K. I is the direction of V and minus K is the direction of B. So minus will get out of the cross product. So I cross K. Mark it as first equation. Okay. Now reminding the cyclic property of cross products. Okay. You have also learned in 11th class. Cyclic property of cross products. I am reminding here. So what is that? I cross J is equal to K cap. J cross K is I cap and K cross I is J cap. This is cyclic property. We are going from I to J, J to K, and K to I. So I cross J is K, J cross K is I, and K cross I is J. Okay. But the reverse of this is not possible, is not same. Okay. So they are not commutative. Similarly, if I cross J is K cap, then J cross I will be minus K cap. Okay. It will change. Result will change. Direction will change. So I cross J is K cap. So J cross I will be minus K cap. Similarly, J cross K is I cap. So K cross J is minus I cap. K cross I is J cap. So its reverse, I cross K will be minus J cap. Now, in the first equation, it is given I cross K. So its result will be minus J cap. Okay. So equation 1 becomes F vector will be equal to minus E minus VB and I cross K is minus J cap. Okay. Now there are 3 negative signs. 2 negative sign will get cancelled out. 1 negative sign will remain in the equation. So F equal to minus E VB J cap. Okay. This negative sign will go to the direction. Okay. So F vector will be equal to EVB. This is the magnitude of the force and minus J cap. This is the direction of the force. What is minus J cap? J cap is Y axis, positive Y axis, minus J cap is negative Y axis. Okay. So now force on the electron will be in the negative Y axis. Which statement is it? B statement. The electron will experience magnetic force along negative Y axis. Got it? Now, therefore, the electron will experience a magnetic force along the negative y-axis. Direction of magnetic force can also be found using right-hand rule for vector products. Okay, that we have found using cyclic property of vectors. Okay, it is also important to know about the cyclic property of vectors because somewhere you cannot apply the rule. It is difficult to apply the right-hand rule. So you can find using cyclic properties of vector. Okay, but you can find also using right-hand rule for vector products. Since there is a force acting perpendicular to the velocity, this magnetic force is perpendicular to the velocity. Velocity is in positive x-axis and this force is in negative y-axis. So they are perpendicular. So only the direction of velocity of electron will change, not the magnitude of electron will change. Only direction will change. So due to which the force will cause the electron to move in a circular path in the xy plane, clockwise when viewed from the positive z-axis. If we view from the positive z-axis, the motion of the electron will be now circular in the xy plane. So E statement is also correct. The electron will move along circular path in the magnetic field. So correct options are B and E. Okay. Next question. An electron is allowed to move with constant velocity along the axis of current carrying straight solenoid. Okay. So in the current carrying straight solenoid, direction of magnetic field is along the axis. Okay. So electron is allowed to move with the constant velocity along the axis. So electron is also allowed to move along the axis with constant velocity. The electron will experience a magnetic force. There are 5 statements again. The electron will experience a magnetic force along the axis of solenoid. The electron will not experience magnetic force. The electron will continue to move along the axis of the solenoid. The electron will be accelerated along the axis of solenoid. The electron will follow parabolic path inside the solenoid. Okay. Choose the correct answer from the options given below. B and C only, A and D only, B and E only, and B, C and D only. Okay, I will give you some time to think about it. So don't go anywhere. There is one very important question at the last. This is second last question. After that, one more question is there, which is very important. So correct option is A, B and C only. Okay, so using concept 18.9, for a long straight solenoid, the magnetic field lines are parallel to the axis and uniform inside. Okay, we have studied in the solenoid topic that magnetic field lines are parallel to the axis and uniform inside. So magnetic force F on a charged particle with Q moving with velocity V in a magnetic field is given by F is given by Q V cross B. Since magnetic field is along the axis, electron is also moving along the axis. So velocity and magnetic field will be parallel or anti-parallel. There are both cases. It can be parallel, it can be anti-parallel. If electron is moving in the direction of magnetic field, then parallel. In the opposite direction to the magnetic field, then anti-parallel. But because both are moving along the axis, magnetic field is along the axis, electron is also moving along the axis, so V and B will be parallel or anti-parallel. It means cross product will be 0. Okay. So electron is moving with constant velocity along the axis of a solenoid. The velocity vector V of the electron is parallel or anti-parallel to the magnetic field B inside the solenoid. Hence, angle between V and B is 0 degree or 180 degree. Okay. Magnitude of magnetic force on electron is now given by F is equal to Q V cross B mod, which is QVB sin theta. Theta is 0 or 180 degree. So in both cases, sin 0 degree is also 0, sin 180 degree is also 0. So force will be 0. So that means since no net magnetic force is acting on the electron inside the solenoid, so it will continue to move along the axis of the solenoid. So which statement is correct? Second, B statement, electron will not experience magnetic force is correct. And third statement, electron will continue to move along the axis of the solenoid is also correct. Okay, so both statement B and C are correct. Okay, so our last question, and this is important question. Two charged particles have same kinetic energy, are allowed to pass through a uniform magnetic field perpendicular to the direction of motion. Means angle between V and B is 90 degree, already given. Okay, and they have same kinetic energy, two charged particle. If ratio of radii of their circular path is 6:5 and their respective masses ratio is 9:4. Okay, so ratio of both the radii of two charged particle is circular path of two charged particle are given 6:5 and ratio of their masses are also given 9:4. Then the ratio of their charges will be, okay, that thing you have to find. Now force experienced by both charges will be QVB sin theta, because V and B is perpendicular. It is given in the question that it is moving in uniform magnetic field perpendicular to a direction of motion. So theta will be 90 degrees. So force will be QVB. Okay. So options are 8:5, 5:4, 5:3 and 8:7. I will give you some time to think about it. So let's see the solution. Correct option is B, 5:4. Okay, using concept 18.9.1. When a charged particle moves perpendicular to a uniform magnetic field, it follows a circular path. Okay, that thing we have studied. The radius of the path is given by R is equal to mv by qb. Mark it as first equation, where m is equal to mass of the particle, v is the velocity of the particle, q is the charge of the particle, and capital B is magnetic field strength. Okay. To solve this question, we have to modify the expression for radii in the terms of kinetic energy. Okay. So in the question, it is given that they have same kinetic energy. So we have to use that thing that they have same kinetic energy. So we have to modify the expression of radius of the circular path in the form of kinetic energy. Okay. So to do that, firstly, we have to find the kinetic energy expression. What is the kinetic energy of the particle? So it is given by half mv square. Okay. So v, by which from this we can find the v. What is the velocity in the terms of kinetic energy? So v is equal to root 2 kinetic energy upon m. So mark it as second equation. we will put this expression of velocity in the radius equation. Okay, in the radius mv by qb, we will put the v as this second equation. Then we will reduce the expression of radius in the form of kinetic energy. So put equation 2 in 1, we get R is equal to mv by qv. So put v as root 2 kinetic energy upon m. Okay, so R is equal to 1 by qb. So we will bring this m in the root, so it will become m square. Okay, so after simplifying this, after simplifying all this, you will get R equal to 1 by qb root 2m kinetic energy. And after, we have to find the ratio of their charges. So in the form of charge, it will become q is equal to 1 by rb root 2m kinetic energy. Mark it as third equation. Now we have find the equation for the charge. Okay, we have to find the ratio of their charges. So we have reduced or simplify the equation in the form of charge and kinetic energies. Okay, so both particle have same kinetic energy. It is given in the question. So kinetic energy 1 equal to kinetic energy 2 equal to kinetic energy. Okay. Also, both particles are moving perpendicular to same uniform magnetic field. So B1 equal to B2 equal to B. Okay. Now using equation 3, expression of charge for both particles is as Q1 will be equal to 1 by R1. B is same for both particles. So we are using B. Root 2 M1 kinetic energy is same for both the particles. So we are using Ke. Mark it as fourth equation. And another Q2 is equal to 1 by R2B root 2M2 Ke. Mark it as fifth equation. Now we will take the ratio Q1 by Q2 because we are asked ratio of their charges. Okay, the ratio of their charges can now be given as Q1 by Q2 equal to 1 by R1B root 2 M1 kinetic energy upon 1 by R2B root 2M2 kinetic energy using 4 and 5. Okay, after simplifying it, you will get Q1 by Q2 equal to R2 by R1 root 2M1 kinetic energy upon root 2M2 kinetic energy. Okay, so after further simplifying, it will become Q1 upon Q2 equal to R2 upon R1 root M1 upon M2. Okay, now what is asked in the question? Ratio of their charges. Ratio of their radii are given. Ratio of radii is given 6 ratio 5. Ratio of masses is given 9 ratio 4. This is all we want for ratio of charges. Okay, so mark it as 6th equation. Now we are given, what is given? R1 by R2, 6 ratio 5. Also M1 by M2, 9 ratio 4. So put this two ratio in the 6th equation. So equation 6 will become Q1 by Q2 equal to, so it is in the expression it was R2 by R1. Okay, so we are given R1 by R2 6 by 5. So put it as reverse 5 by 6 and in root M1 by M2 9 by 4. Okay, so this 9 by 4 after coming out of the root it will become 3 by 2. Okay, so Q1 by Q2 will be equal to 5 by 6 into 3 by 2 which is equal to 5 by 4. So ratio of their charges will come out to be for both particle is 5 ratio 4. So this is very important type of questions which is generally asked in the JEE or NEET. Okay, so thank you. I hope you enjoyed the session.